announcements. So I'm going to switch welcome everybody to the ESIP Cloud Computing Cluster Knowledge Sharing Session for May 24th, 2021. So I'm going to go ahead and get started with announcements. And then I'll pass it off so I'm switching the agenda from, if you're really paying attention. So can you guys see my Google Doc screen?
Yes.
Okay, cool. I'm going to switch it up a little bit just because I want to make sure that I get in a few announcements, and then I'm going to pass it off to Martin Durant for the presentation on fsspec and reference file system, and then we'll do discussion questions. So first, some logistics, basically. So obviously we have this recurring knowledge sharing session, which is the fourth Monday of every month. I've had some requests for a Google Calendar event, which I have and some of the other organizers have on their calendar, that just has, just the recurring event and the Zoom link. So if you want an invite to that, just send me a message either in the chat here or in the Slack channel, the Cloud Computing Slack channel. Additionally, I wanted to just say, as sort of an FYI, I'm going to be holding working sessions one time a month on the second Monday of every session. So basically, like, there's a bi-weekly schedule, and the fourth Monday of every month is this knowledge sharing session. And then the second Monday of every month would be this working session, which is basically a way to do this sort of like working collaboration on different areas of actual work product that we want to come out of this cluster. So in the first instance, that was a few of us getting together, just talking about the agenda for the summer session, the ESIP summer session that's coming up in July. So the next session, which would be basically 2 weeks from today, would be any sort of additional coordination that we want to follow up on with potential speakers for that session. Another idea that we had that we wanted to do as part of this computing cluster is a sort of hashtag cloud clinics part of the ESIP summer session. So I want to start coordinating around what that could look like, both for the summer session and in the future. So if you're interested in any of these topics, just send me a message on Slack or in this Zoom meeting chat. Again, as I mentioned, there's the ESIP summer session that's coming up. So it's called The Saga Continues, and you can look that up on the ESIP summer session site. Yeah, are there any other questions or announcements about any of that so far? Silent acknowledgement, my favorite. Okay, cool. So I'm going to pass it off to Martin Durant. Yeah, welcome, Martin.
Hello. Can you unshare or give me permissions or whatever it is so that I can share my screen?
You should be able to share your screen.
Yeah, it's coming. Okay. You can see it, right?
Can.
Okay. So I'm going to give an introduction to reference file system. This is meant for discussion. And some of you, particularly if you've been at the Pangeo meetings, will know some of this, but I'll try and go through it all anyway. So the background is we all know what HDF5 is, and there's an awful lot of data in HDF5. It's not the only archival array storage format out there, but it's probably the most volume as far as the people here are concerned. And we can talk about other possible binary storage afterwards. And there are things that are around, for example, being pushed by Pangeo, like Zarr, which came out of Python, but is actually multi-language as well, that is particularly useful in the cloud compute context. The reason it's useful is because you control the chunking and compression of your data set, and each of those chunks becomes a separate file on the file system. So if you want to process it just some subsection or process all of it in parallel, then you can access all those different files independently. So Zarr is super simple and great for this kind of job. So we have a load of data in HDF5, which is somewhat becoming better on the cloud, but it's still it's a long way to go. And so something like Pangeo Forge was set up, and indeed Pangeo people were already doing this, and other people besides. Let's transform our HDF5 archival data into Zarr so that we can then do analysis on it using, for example, Dask or other parallel systems that are out there in a cluster on the cloud. The obvious downside of this, if this is that you have to process your HDF5 file and you end up with a copy of all of your data. And we'd rather not do that. So reference file system that I'm talking about today is a way to view your original data in situ in its archival format and be able to get all the benefits out of Zarr when you read it. So for the HDF example, and again, this is not going to be the only binary storage format, but it's the one I did first. It's the one that we set our goals on first. So it stores something like this. There are binary blocks of data that are gray in this picture, and there's metadata, which is purple. The actual arrangement of these within an HDF5 file varies wildly depending on how that file was constructed. You often have quite a lot of the metadata up front, but actually sometimes it's exclusively at the foot of the file. Sometimes it's interspersed, whatever. But the important thing is that the binary blocks, so these gray pieces like this, that are scattered through the file, do form contiguous binary representation of a chunk of an array. This means that if you have an array that is a normal NumPy-like buffer, or a C buffer, if you like, so a contiguous stack of bytes, each of which maybe it's 16 bits per value or whatever it may be, but you have this block, that would be the memory representation. And then the thing that you have within the file itself is you take that C-level representation, you do some encoding, some filtering and compression to it, and that's the thing that's stored in the file. So you can imagine, if you know where this is in the file, you can reverse this process, you can decompress, decode, and you will have your C array buffer back, and you don't need to know anything about HDF5 to be able to do that. You just need to know where in the file it is. So we can, in fact, if we have a set of offsets, we can represent this very same file as a set of references. This is the name that we'll be coming back to. So reference file system refers to this referencing system where we say this block up here, I'm going to refer to that as this file path times 0. And this block down here, I'm going to refer to that as this file path time 1. And I'm going to give Zarr the means to be able to decode and decompress those chunks into arrays, which is what Zarr would normally do, but Zarr normally expects its files to be discrete separate files. And here we're fooling Zarr into loading pieces of an HDF5 file and regarding that instead as separate files. That's the essence of what reference file system does. I will demonstrate it in a moment. Once you've done that, you can go further. You can view, now all of these, this is a bunch of HDF5 files on the left here. I've shown them with the same layout just because copy and paste is easy, but they could all have different layouts within them. And now if instead of just time/0, we have time 0, 0, 0, 1, 0, 2, 0, 3, time 1, 0, 1, 1, 1, 3, 1, 2, 1, 3, whatever it may be, you can refer to all of the chunks in all of the files, put them all in a single set of references, pass them to Zarr, and to Zarr, this bunch of HDF5 files will look like a single Zarr dataset. And you could have as many dimensions as you like. So reference file system encodes this idea. For any path, you have a couple of possibilities. You may have some text data, and this is typical for the Zarr metadata blocks. They're just JSON, so that's normal text that we can encode very simply. You might have binary data, and that may be short coordinate runs, for example. It's better to put them into your references file than to have to extract small pieces from the target file. And then the more general references can be a URL to a file or a URL to a part of a file. Those are the things that we refer to as references and get stored into a single JSON file for reference file system to read. So reference file system is an fsspec implementation. It's a backend just like any of the others, which means that you can use it in conjunction with anything that can deal with arbitrary Python file-like objects, which is quite a lot of things these days. And a number of projects out there have explicit integration with fsspec. So if that exists, then you can use a reference file system where otherwise you would have used a local file system or S3 or whatever it may be. When you've done that, you will get parallel access and concurrent IO. And in addition to that, you can, I will demonstrate these features rather than talk about them too much, but there are extra things that you can do to speed up and reduce the size of the references that you have to store. After you've done all of that, once you know where your references are stored and you load it with Zarr, it's actually just as good as if you'd converted all of your HDF5 data into Zarr, only you don't need to have done that step. You don't need a copy, you just need the references themselves. And furthermore, as I mentioned, you can use this system to make an ensemble data set of many HDF5 files, and you can make multiple views on some subset or some superset of a set of files. You can mix and match however you like to make new Zarr datasets without copying the original data. So something like Pangeo Forge likes to make use of this kind of thing, and we'll come back to that in a moment. But first, I'll show you my local example, which will work because this is on my local disk. And then Rich, if we have time, we'll show you a live demo if you're ready for that, where we actually do some processing. So I'm just going to show you what the references look like and how you can open a data set, but I won't do any processing because this is just on my laptop. So here we have a template file. I'm just going to show. So this is stored in JSON, which is the canonical form. It's human readable, which is good. And it includes, well, some JSON stuff, which means that we can load it and we get this references dictionary, which we can look into. So this contains a references subdictionary, and that contains a bunch of keys. So here, for example, is one key. Those that have worked with Zarr before will recognize this is the top level group key of a data set, and it just has this little JSON piece in it that's encoded within the global JSON file. So that's there, this key, and that's going to be the file name that we can access this by. And we have more of these. Here's a slightly larger JSON blob. This is in one of the arrays. So it's in a subfolder called time, and it indicates the type of array that's going to live in this subfolder. And here's some Zarr specific things that tell you about the shape and size and compression of that piece. And we also have some data. So this is, again, those that understand Zarr will recognize that this is one of the data blocks. And in this case, this is still stored within the global JSON file, and it's been encoded using base64 because this is a very short array. So it's worthwhile doing this. And then we have some more general ones. So here we have the elevation subdirectory, one of the data keys within there. Looks like this. So this is a list. It has some string part, it has an offset, and it has a size. And the string part is a templated thing that will be filled in from some other stuff that's also in this JSON file. This is just an optimization to keep the size of the JSON file smaller. This whole string could have been in here, but we choose to use this templating approach in this case. So the end result of all of that is that we can open a data set. This will take a second. There's an interesting note here is that I have stored these references on Google, but the actual location of the data is on Amazon. This is totally fine. You can do this kind of trick with reference file system. So if you're in the business of creating these references, then you can store them wherever is convenient and they won't be too big. But this opened just fine. This was my alternative in case Google was down, which it was a couple of days ago, so that I could load exactly the same through from my local copy of the JSON file. So I don't need to do that now, but having opened it, it looks like this, a normal X-ray data set with a load of things in it. And this is referring to a data set which is a gigabyte big, which is not something I would choose to download live here during this talk. But you would still like to process this kind of thing in parallel if possible, and you'll see all of these things here. I expected it to tell me that these would ask arrays. They will be, and so you can load this thing in parallel. So that's it for the local live demo. We could look at the actual implementation. It's interesting to play with this file system. So I can open the file system itself. But I guess I'll just open this and then leave it for if people have questions about it. So this is the thing that you have, and you can do normal file system like things on it. So there's the top level directory. Okay. Rich, do you want to do your demo now, or should I talk about the discussion points first?
Yeah, let's do the other demo, and then yeah, you can wrap up.
Okay, go ahead.
Sure. Okay, so we're actually using this. The USGS, we just gained the ability to publish our data sets, and we have these trusted digital repositories where we're required to publish our data. And one of them is called sciencebase.gov, which was previously sort of a database kind of thing and file system, and now it's moving to the cloud. So we're actually storing our data on S3, and we have a lot of model output that we want to publish. And so we have a lot of people who use MATLAB, and they want to access NetCDF files, not Zarr data sets. So we produce NetCDF files. So we thought, okay, let's actually test this out on a real case. So we have a simulation of the Matanzas breach. We do coastal oceanography. So we have this data set that we use this technique that Martin just described. And so this is actually like a comparison of accessing the data straight using the H5 NetCDF library, which was how you would normally do it if you didn't have this approach. So here I'm just importing Xarray and fsspec, and here I'm have two file systems. One is anonymous equals true, which is we actually distribute our data on ScienceBase as a fully open public bucket, and then we have a requester pays bucket that's on the ESIP cloud where I have the Zarr data set. So we're not publishing the Zarr data set as part of our USGS publication. So here we have this this link to our ScienceBase USGS bucket, Breach Matanzas, and we're going to open it up with H5 NetCDF, right? So this is how you do it. If you were just somebody gave you a NetCDF file and S3 bucket, and you didn't know how to use if you didn't have this sidecar JSON file, you'd open it up. So we're just opening up the data set now, right? We're just reading the data. We're just reading the attributes and the coordinate data, and it takes 13 seconds. And now we're going to load a particular variable, the sea surface height, and we're going to extract all the time values from a specific spot in this XY grid. We're going to take the mean and tell it to compute. So we do that. This is actually loading. Maybe I should have showed how big this data set is actually. So ds zeta. and bytes. 26A. So yeah, so it's it's the three gig. Oops. Is that right? What did I do there? Yeah, so 346 megabytes. That's not too big. Wait a minute, I can't be right. Did I do something wrong here? Anyway, so I took the so that took 13 seconds to compute the mean. So this is like, so it took 13 seconds to open the data set and then 13 seconds to do the computation. This is just with a single core here. So 13 seconds to open the file, 13 seconds to compute the mean using the standard HDF5 library, which is what you're using when you do H5 netcdf. So now we're going to go to using what Martin just showed you. We have this JSON file that's also sitting in our S3 bucket. So we can basically open this up using the Zarr engine. So we're going to open this up, and instead of taking 13 seconds, it takes just 1.8 seconds because we're just loading the metadata in one shot. Everything is right there. And now let's do the same computation on the means. This is the same netcdf, the very similar CDF file, and now it's 5 seconds. Roughly 2 to 3 times faster than just accessing with the HDF5 library. So for very little, all we had to do is create that JSON file. And so it's, anybody can do that, right? I don't have to go back to the data provider. Like if I could create this, if USGS hadn't provided it, I could have just created it and then used it myself. So now we're going to actually open the same data set in the same region, not on USGS bucket, but in another bucket on US West 2. And we're going to load this thing in with consolidated metadata. It's really fast. It's like less than a second. If we do this computation again, we get 2 seconds. So in this case, actually, Zarr is a little bit faster than the FS file reference system, but really depends on, I don't know, Martin, if you have ideas about why that may be in this particular case, but basically each data set.
Last time you tried it was the same.
yeah, it actually, if we did this a bunch of times, actually S3, we probably need a longer test maybe, than this very short one that's for demos. But it is pretty variable. But it's much faster. The main point is it's much faster, and and for other data sets, yeah, it was basically the same or even a little faster than netcdf. And so, and this is just to show you that you really should use consolidated metadata, at least especially if you're using one core on. If you load with if you don't use the consolidated metadata, it takes a really long time to open the file. In this case, there's a bunch of variables, something like over 100 variables, and yeah, it takes 20 seconds, and then this should take about the same. Yeah, it takes about 2 seconds. So, and actually, Martin, I don't know whether you showed actually using the unconsolidated metadata, but do you also do the consolidated metadata, or maybe it doesn't matter?
Well, what for opening via reference maker, it makes no difference.
Yeah, okay.
A reference file spec, because it's all just in memory.
Right. Okay, that makes sense. Yeah. So basically, way faster to open the file with the file reference system, 3 or 4 times faster, at least for this case, than the HDF5 library. In this case, reading with Zarr was still a bit faster. And then, of course, if you're reading Zarr, you should use consolidated metadata so that you're reading it in one shot. All right, so back to you, Martin.
Okay, so that's the current situation, is that this works. You can make references for any HDF5 file, or indeed any TIFF file if you have those that's been added in the TIFF file project. It will also work for other. There's basically most array storage does this same technique. It takes your C buffer and it does some kind of encoding and compression on it and stores it in a blob into a file. And if you can read the file, read enough of the metadata to know where those blobs are, then this technique will work for you. Now we need to make those scanners that can go through such a file and find out where all the blocks are for the various binary formats, and that's not exactly a small job, but it's not too complicated either in most cases. So we can have Zarr be the access point to a large number of binary array storage files without having to copy them again. So there's a lot of future in this idea, and we need to figure out priorities and test cases. The thing that's hard about it is figuring out if you have multiple files that you would normally open with X-ray Open MF dataset, where each of the chunks from each of the files fits into the final ensemble. That's it's something that can be logicked out. We can find out how you should do that in a totally general way, but we don't have that yet. And X-ray does this already internally somehow in some magic way. If it knows where to put all the pieces. So we need to hijack that logic and make the references all be in the right place. In effect, we are doing an upfront consolidation, if you like. The reason that it's faster is because we don't need to get all the little pieces from within this HDF5 file. We already have them in one place because we've done it once. It's the kind of thing you only want to do once because you will be generate it once and read it many times. The spec itself for how these references look is in the repo on the screen. So it actually has a fairly well thought out, well prescribed definition of how this thing should look. It's already possible now. The JSON is the sort of canonical storage described there, but we can store the references themselves in a more efficient binary format, which will be important as we make really big data sets. We don't want to stick to JSON always. It will be slow and large eventually. For the time being, for the kinds of sizes we're dealing with now, where JSON is actually faster than bothering to fire up a Zarr or Parquet reader. Something that I saw that Peter was on the call. So Intake Informatics Lab has a different path for doing this kind of thing, but I realize now how it can be put into the reference file system methodology also, which is basically if each of our blocks is a whole file and we don't want to refer to the internal blocks of that separately, then that effectively says that the decoder that we want to use is the HDF5 library itself or the GRIB library, CFGRIB or whatever. You can do this same trick and open with Zarr, and basically you make a custom filter that's going to translate the part of that file that you want into the array representation. That means you do end up downloading whole files, so you don't win when you want to make subselections, but you might win when you only need some of the files from an ensemble. Then Zarr would give you the way of selecting those pieces, even in that case. And it would still do that fetch in parallel. And then once it's on the local disk, it's fast, of course. Yeah, so the last point here is that here we're scanning a bunch of files to figure out where things go and looking at their coordinates. You don't necessarily need to do that. Often the information of where each file should go is actually encoded into the path name for that file. So potentially, if they all have the same layout, then you don't need to do any scanning at all. That would be very nice. That doesn't exist yet, but it's the kind of thing that is already happening in the recipes of Pangeo Forge, and Intake also has a similar concept for data files such as CSV. It's very common to store them on a path convention. And so it should happen here too. We just don't really have example data sets to figure out the logic of how to do it yet. But it's all doable. It's all there, ready for it's open territory, ready for conquering, let's say. It does raise some questions that we can come back to. So is this Fuse? It's sort of like Fuse. Fuse is for those that have never used Fuse, it's a little bit out of fashion these days, I guess. It's a way of mapping some arbitrary storage solution into the file system of your Linux kernel. And you could already actually do that for fsspec. You could make remote files appear as if they were local by using Fuse. And this is sort of doing a similar thing. It's a virtual file system, but it doesn't need to work via the operating system. It just needs Python to work. And that makes things a lot simpler. In particular, Fuse is kind of brittle, I have found, and slow. So although it could enable certain things to happen in the past that weren't possible without it, I don't think Fuse is a thing for the future here. What about other services? So HSDS claims to solve the fast access to cloud data HDF picture, but it doesn't, is I think the short story, for multiple reasons. A, it's not necessarily fast. B, you need a service like a node, a data node that's going to do this thing for you. It's going to talk to HDF files and it's going to find out the pieces and channel them to you. We don't need any of that. This reference file system doesn't need a server, doesn't need a service. It just needs those references, which can be stored wherever you like. There are other ideas around HDF5 files of making them fast, chunking them right, various other things. These probably will actually help reference file system too, but it doesn't need them. The point is that we have all this archival data and we just want to access it somehow. The references we're storing in JSON files for the time being. The examples are on the order of 100 kilobytes, so essentially nothing compared to the size of data that we're usually dealing with. You could make them on the fly the first time if you wanted to and cache it. That's if you, the researcher, are going to be accessing the same data set many times. That's a reasonable thing you might do. But I think for the time being, we're going to be on the side of creating these reference files and putting them in a public place so that anybody can access those files easily. But there's some wiggle room on that one. And then finally, the call, which was this line, to make it run is kind of complicated, right? There's a few things that you need to know to make this happen. So the question is, could it have been simpler? And maybe, but maybe that wouldn't be as flexible. And since I also happen to work on intake too, I would say it doesn't matter because you can encode that whole call into a catalog so that the end user doesn't need to know about it. They don't need to know that the data is stored in like the references in one place, the data in several files in another place maybe, and they don't need to know what specific invocation they need to use to be able to access the data. It's just going to work. So in conjunction with cataloging, I think this is not a problem. So that's it for the presentation, and we can go to questions and discussion.
Awesome. Thank you so much. Yeah, do other folks have questions for either Rich or Martin?
I have so many. First of all, thank you. This was awesome. I'm glad to see. I think this has been about a year and a half or a year and a quarter since I saw the first movement on this, and it's great to see it getting traction. Very nice work. So a couple things, questions, some little caveats too. I guess maybe working backwards, you'd mentioned the index files being small compared to the data files that you're working with. I want to throw out a little bit of caution there just because I have encountered files where I think ISAT2 in particular was, they have like 2 gigabyte files in 10 kilobyte chunk sizes, which can obviously overwhelm your JSON parser if you're not quite ready for it. But that's kind of just a little thing.
Yeah, the binary storage in Parquet would still work pretty well. So Parquet would be good at storing the offsets and sizes, which are just numbers, exceedingly well. And if the same file name occurs many, many times, then the templating will save you from having to store too much in bytes there.
Oh, excellent. That's great to hear. I thought I saw it on one of the early slides, but do you have, are you doing optimizations for if chunks are contiguous in the file, fetching them in one go?
So no, I went to this talk by H5 Coro last week, and
Yeah.
they specifically consider that case and do a lot with it. And we could, where fsspec is in the right place in the machinery to be able to join those calls together, but it's definitely not there now.
Awesome. Yeah, I was going to actually ask about the H5 Coro work because it seems like almost getting some healthy competition here, which is probably good for both cases.
Yeah, H5 Coro is very specific to what it is that they want to achieve, and probably there's no way that reference file system can match it if they've pulled on all those levers. And so we're more general. We can deal with multiple HDF5 files or multiple things. They don't have to be HDF. In fact, you can even have heterogeneous types of files in the same data set plausibly. I don't know if in practice that would ever happen. To be able to support all of that means that we won't be able to reach too deeply into HDF5 to figure out some of those optimizations.
Cool. The last one, and then I'll stop hogging the mic. One thing that I've seen too, and I haven't done any testing on this, but I think it's worth testing. I was wondering if you had seen anything along these lines. But if you're doing, so ultimately under the hood, this is going to be doing range gets in S3. And what I've seen is that AWS recommends that you byte align you align your reads with how do I say it? If you're uploading a multi-part file to S3, you're uploading the object you're storing as a multi-part file, that the size of those parts that you're uploading is the size that they recommend downloading, or sorry, they recommend you download.
Yeah, I know what you're getting at.
Parts.
I've seen the same thing.
Yeah,
and that's definitely true for streaming a whole file. Here we're doing the model is more random access parts of a file. So there's two cases. The first case is that the latency for the server to fetch the data dominates the transfer. And we have the ability with fsspec to concurrently fetch many files at once. And then the latency is at least shared amongst those many requests. It may still dominate. So that's part of the picture. But you often hope that your chunk size is more favorable. There's nothing you can do about it after the fact if you're not going to rewrite the data. But the very large scale will tend to have more reasonably sized blocks within it. And that means that things like the byte boundaries won't matter. And in any case, you can't control, we don't know what the upload scheme was. These days, S3 allows up to 5 gigabytes in one shot. It didn't used to. It used to be anything over 5 megabytes, you had to use multi, but now you don't. So now there might not be any boundaries in there at all. And in which case, I don't actually know what S3 does internally with that.
Someone asked for the link. I do have it, so I'm gonna drop it in.
Also, we want to make this generic across multiple services.
So I'm not necessarily saying it's an optimization that you would do. I'm just more hoping that someone has done it, because I haven't done the math to find out what the performance difference actually is. So it'd be interesting to look at, especially if you're someone who does control the upload and the internal chunk sizes and those kinds of things, if it makes a difference and how much. But sounds like you haven't done that specific test. Neither have I. Maybe someone out there has.
in these tests in these demos that we showed, the chunk size is somewhere between like 10 and 100 megabytes. Because we did have the luxury of creating this data, and so we wanted to make it cloud optimized, and that's actually still a fairly common use case, I think, and at least until like NetCDF, every application that is built on top of NetCDF supports Zarr. I mean, I guess that it's coming, right? The latest version of NetCDF library supports Zarr.
Yeah,
But
that doesn't mean that too many people will actually be writing those. I will see, we'll see, right? HDF still
right.
in this field is the sort of blessed archival format, and in other fields there are other specific formats
Yeah.
that play the same role.
Yeah.
Yeah. So I guess the point being, like, if you are the archive, or if you control the data you're uploading, there may be some further performance to eke out, or some further user benefit to have by being careful about the combination of chunk size and how you're uploading it. So
Yes, and
that
that's,
requires further testing, though.
yeah, and that will be true for any format type. Right, the chunk size is a
Yep.
critical variable that I don't know in practice for the large institutions that are uploading data, how they make that decision. I mean, it might just be that's how it arrived, and it's a concatenation operation. So
I mean, that is, I think that's usually the case, right? Like for modeling workflows, people run their models and they write their output at, every so often, and they write a 3D field or 4D field, and they take the next so many time steps and they write another one, and then that's what they use, and it's always chunked one in the time dimension.
Yep.
I think we need to work on that, actually, like getting rechunking to be like a standard part of these workflows. Like that should be your post-processing, is like actually thinking about your users a little bit.
And with the H5 Coro work, but also just in general, that the problem of metadata scattered throughout the file and all that kind of thing, that's fixable if you're the one producing the file. But we don't so much focus on that. Anyways, interesting stuff. I've hogged the spotlight enough. Thank you.
So with this implementation,
nice.
was that with the fsspec reference file systems is kind of a noob question, but like with that, does that help with the rechunking question? Like, does this, or do you still need to create if you need a new chunking shape, would you have to generate a new like a Zarr data store? Is that a reason to create a new like an actual Zarr file store, or can you do that with the metadata itself?
So no, the chunks within the remote file are where they are, and reference file system can't change that. We may be able to, as was mentioned just before, we may be able to, if we need several chunks that happen to be close to each other in the target file, maybe do a single read and then pull those byte ranges out rather than issuing many reads at once. And that can help to some extent, but you won't be able to get around the actual layout that's there in the remote file.
Because one of my questions was just, does this type of thing, or H5 Coro obfuscate, make obsolete an actual Zarr file store? But it sounds like both for compression is the one reason I heard Ryan Abernathy give, but also it sounds like if you need a different chunk shape, that could also be an optimization that you are getting with the actual Zarr file store. Is that right?
Yeah, you could rechunk to HDF, and I'm sure some people do that. But if you're doing that step anyway, then that's a good time to pick the file format that suits your cloud nature the best.
I see. So you'd only probably want to rechunk to HDF5 if that's what other users might be more comfortable using. Right.
There might be a case for wanting to do that. Yeah.
I mean, that's what we did with that example that I showed. We had a model output and we rechunked it. We actually wrote it to Zarr and then converted it back to NetCDF because we wanted to use the rechunker package because it was fast.
Right.
The slowest part of the whole workflow was converting it back to NetCDF.
Interesting. Yeah. What did you use to do that?
We just used Xarray and wrote it with a single core.
Right. Okay.
Yeah.
Okay. Chris has a question. If I have, first chat, I think consolidated metadata seems important for this and other approaches of speeding up HDF5 and object storage systems. New questions. How does one control metadata placement? B, are there standard processes for reorganization for consolidation?
So for the A, I have no idea how you write your HDF5 file so that the metadata is all in one place. Obviously, other people don't tend to know this either, because in my experience, that's not the case. But I know it can be done. Maybe the second you start appending to an existing data set, I think the metadata ends up wherever your new data goes, so that you don't move the old stuff around. So I don't know that there is a specific concept in the HDF5 world of consolidating your metadata. There are various indexing things out there that I've heard of. I haven't used them myself, so I don't really know exactly what they do. I suppose that's the B part of this. It has to be doable. I just don't know how. And it would, yes, it would improve even your access time with any HDF5 tooling if you could do that. But probably you're making a copy. So if you would be making a copy initially, but presumably the original archival version needs to stick around because it's in the archive. So even if you've made a better version in the correct format, you probably still can't replace it. Usually, unless you are the archive when you're doing this.
Right. Okay, Chris asks, if I have a swath file with the geolocation in another file, can I create a virtual reference file that puts them virtually together?
I don't know what a geolocation file would look like, but if it's another array or even attributes in the netcdf sense, then you could put them in the reference file system tree, and you would need to know what you're doing or hope that someone's written the code specifically to do this kind of thing so that it appears in the right place, that Zarr and X-Ray will pick it up when they do the read. So I would say, yes, it can be done, but I don't know enough about it to say exactly how.
But I think it's worth saying again that this is really one of the, I think, kind of exciting things. Martin already said this, but we used to use like for these forecast models, that have lots of overlapping times, and we used to use things like the NCML and the threads catalog to create these forecast model run collections, which would give you a virtual view into the data, so you could extract, the data at tau 0 or like the best time series at tau 4 or whatever. This also gives you the opportunity to do that without interacting with the people on this, and we don't need a service, first of all, and also we don't need to deal with the people on the service side, because we can just create our own JSON, reference file systems, and give us whatever view we want through, say, the HER data, which is a bunch of hourly, GRIB files, like 3,000 hourly GRIB files. So to be able to actually just give someone a JSON file or create on your own is a super powerful thing, and so I'm really excited about that.
Yeah, the GRIB format is still stumping me for the moment.
Yeah.
But,
oh well.
I know it can be done. It's the tricky part is for HDF, this works quite well because at least you can read from remote, even if it's not as fast, as performant as you would like it to be. You can scan through the file and find all the metadata pieces so that you know where the binary blocks go. For GRIB, that's not the case. It's a C-level library that requires a real operating system file handle locally. And I'm pretty sure I'm getting towards the place where you can download just enough of the GRIB file so that it can extract the metadata, but not the arrays in the same way. I mean, there is an internal structure to GRIB files that it has these blocks, so you can go block by block at least. Exactly how to persuade the low-level GRIB reader to give you some and tell you where the rest is a work in progress, let's say.
That should,
yeah,
sorry, Rich. That should be built into the GRIB messages, right? So there should be a bytes offset at the end of each header. So you should be able to get the header, then know how far through the GRIB message you want to fast forward to get to the next block of header, which is unhelpfully segregated all from one another.
Yeah, I'm sure it's there. I'm sure it could be done. I just haven't figured it out. And if you could do it, that'd be amazing.
Let me see if I can find some time. Yeah, it's good.
So I was just going to say that, I mean, one of the things that made HDF5 nice, easy to apply this method to was that they, at some version of their library, they supplied a routine that would output in JSON all the byte ranges, right? Like, so that was super helpful. And it'd be nice to have something for the Grib library that did the same.
Yeah, that was going to be one of my questions too. Sorry, Peter, what were you going to say?
Talk to ECMWF, the European Centre for Medium Range Weather Forecasting, about that. Perhaps I think they have some sort of control is exactly the wrong word. Like oversight of Grib. They might have something like that that'll do it.
It's the same story for many file formats, actually. It depends. It seems to depend on how specialized the file format was in the first place. So for example, I come from an astronomy background, and the FITS is a file format that has been around since the 80s, I think, and is reasonable in this sense. You can separate out the header and byte range. It has some unhelpful features that it has an internal heap and pointers that is not commonly used. So if a file had that, it wouldn't work. You would be pretty much lost. But in the normal case, which is imaging, then you can use it just fine. And that will be true for quite a few file formats. The one missing piece is the encoding of your C buffer into whatever's on disk. And there aren't that many options out there, but there are the ones that explicitly exist in Zarr so far are the ones that were important for Zarr. So we will definitely come across data that has an encoding we don't yet know, and it would need to be implemented in Python probably to get it to work. And that happened recently for byte shuffling, and there may be other ones out there that, well, as the formats come in, as the encodings come in, we'll deal with them.
Yeah, I definitely think one of the things that we've also talked about is creating and like having a repository of these examples. So actually, Martin, I was curious if you have an example of how you created the Zarr metadata for the example the local example that you gave. Same thing for Rich with your example. I think starting to compile those examples, even if they are very implementation specific, would still help people.
Yeah, the fsspec reference maker repo has a couple of examples built right into the HDF module.
Oh, that's good to know. File, what is it called? Sorry.
fsspec reference maker.
Reference maker. Okay.
I think I have the same question, which is there isn't currently a generic way of figuring out how the JSON files that describe, so the references are made, is there? As in you have to, as a user, generate.
I think that would be a good new tutorial to host at some point. Like somebody goes through and says, here's my netcdf files. Let's look at what they look like, the metadata looks like. Let's go through actually using the reference maker.
It's also worth mentioning that like Martin gave me his code that actually generated the JSON for the file, the example I showed, but I wasn't able to run it because I didn't have the right environment. Like I didn't have the latest,
everything is cutting edge, of course. Yeah. I mean, actually the first code on this was in November, I think. We were talking about it for a while, but it's all very new. If I go down to the bottom of here, we have a couple of examples. So here's the simple example. This was the Ike data, right? Was the first one that we did.
Yeah, Hurricane Ike. Yep.
Yeah, and so it's pretty short. You don't need to know too much for this, and this returns you the JSON thing that you need. And there's a couple of examples. Here's another one with multiple files, and it creates a single archive with multiple JSON reference sets in it. And then the final one takes a set like that, and it turns them into a single output JSON set. So there's like this is a tutorial without words.
Yeah. Okay, this is cool. If you this is in reference maker. You can find this. It looks like in the intake library or intake org fsspec reference maker. Okay, cool. Yeah,
I
sorry,
was
go
just
ahead.
going to say, it just reminds me of some developer told me once, they said, why do you need documentation? Just look at the code. The code tells you what's actually doing.
Well, that's a philosophy, right?
It is here.
Um, okay, well, with that, we're almost at time. I feel bad. I didn't really give any time if anybody else has any announcements for the group. Okay. Martin, this was great. If anybody else has suggestions for speakers for future sessions, one idea I had would be really cool if somebody talked about GRIB and how GRIB is being used. The theme of this quarter is data formats, but don't feel like you can be constrained by that, maybe just be inspired by that. So yeah, if you have any suggestions for speakers for the next session, which will be in June, please let me know. And yeah, otherwise, I'm just going to plug again the ESIP summer session, and let me know if anybody else wants a Google Calendar invite to this particular recurring meeting. I think that's it. So
Great.
thanks, everyone. Have a good week.
Thanks, Amy.
All right, bye.
Thanks all.